Hello everybody. In this picture you see the airport of Geneva, and here is the CERN with this accelerator almost 30 kilometers long. We want to find out how do they accelerate the particles, and the answer is they do it by electric and also magnetic fields. This is today's topic. The title, of course, reads a little bit different. It's about the homogeneous field. The homogeneous field is a very simple type of electric field, and we want to see how to produce it. The easiest way is if you take two metal plates and you charge them positive and negative. So here a positive plate and a negative plate. So you put them parallel, and if you now think about a point charge, a positive one, a test charge that you put here, then this will be repelled from the positive plate and attracted by the negative one, so it will go to the right. And this is then the direction of these particles and therefore the direction of the electric field. This is also true for more or less the whole part in between these two plates. If we go further away, these lines will become a little bit bent. So maybe like that. The inside here is called a homogeneous field. A homogeneous field is if it's the same magnitude, the same strength of the field all over, and if it has the same direction all over. This is true within this central part here. It is not true anymore for this outer part, and this portion of it is called also fringe field, while here this is the homogeneous field. We might also put some arrows here to give the direction of these electric field lines. If you have these two metal plates parallel to each other, they have been given a name. We call this a parallel plate capacitor. What can you do with a parallel plate capacitor? I show you an example. Ich habe hier die Influenzmaschine aufgestellt. Diese erzeugt hier hohe Spannungen, Ladungen, und diese beiden Kugeln oberhalb werden nun aufgeladen und wir sehen dann ab und zu eben eine Entladung in Form dieses Blitzes, der hier von Kugel zu Kugel geht. Ich will nun diese Ladung auf diese Platten hier übertragen. Wir sehen hier zwei Metallplatten, es ist ein Plattenkondensator und wir verbinden diese beiden Anschlüsse hier mit dem Hochspannungsgerät. Zwischen diesen Platten aufgehängt ist eine leichte metallische Kugel und wir schauen, was hier passiert. Let's now come back to CERN. In this huge tunnel, there are tubes inside, and inside these tubes there are charged particles, can be electrons or protons, that are accelerated. And how are they accelerated? Well, it's just in the same way that we have seen. It is with electric fields. Sometimes they also use so-called magnetic fields, but we focus here on electric fields. Inside this tube you have sections, and these sections can be charged positively and negatively. We start with an easy example and say we have a positive and a negative part. We assume that we have a negative plate and an electron starting in the middle. So usually the electron is already on its way. So it's coming from the left side, entering the hole and then moving away. Since the electron is negatively charged as well, it will be pushed away by this negative plate, negative, repulsive. And if I put a positive plate on this side, again with a hole in it, it will be attracted by this positive plate. We could also say that the electric field between these two plates is accelerating the electron. Let's calculate this. The electron experiences a force, which will be to the right. And this force is given as the charge times the electric field. The electric field is opposed to the force, but the charge is negative, therefore for the direction it will be to the right. We could do an example here. So the electron starts at plate A here. Let's assume it is just at rest, and it will experience a force, therefore it will be accelerated and will end up at plate B with a certain final velocity. So what is this final velocity? The easiest approach is if we use conservation of energy with an external force. The final energy is equal to the initial energy, but here we have added the force by electricity, so it is plus the work done. Final energy will be kinetic energy, which is 1/2 mv squared. Initial energy is, if we say the electron was at rest, 0, and the work done is force times displacement. The force we have seen, it is the charge multiplied by the electric field, and S is here just the spacing in between these two plates. We can resolve that for V. So I have to multiply both sides by 2 first. Then I have to divide by the mass on both sides. And then I have to take the square root out of it. We can give some numbers. The electric field could be 20,000 Newton per Coulomb for the distance 5 centimeters. The mass of the electron is always the same, and the charge of the electron is always the same as well. It is this elementary charge so we can put in the numbers. First, let's have a look at the units. The Coulomb drops. We have to remember what is a Newton. A Newton was kilograms times meter per second squared. Then we see that the kilogram drops and we are left with meter per second squared times meter, so it's square meter per square seconds, and square root out of that is meters per second. And if we put this into the calculator, we get 1.9 times 10 to the power of 7, which is quite fast. So these numbers are what you can do in a lab, for example. So these are typical fields and distances. And if we compare that with the speed of light, which is 3 times 10 to the power of 8 meters per second, we can see that it is 6% of the speed of light. We have now seen how they accelerate charged particles. They have to be charged, otherwise it's not going to work. So therefore they just use protons and electrons, for example. Never neutral particles. You cannot accelerate them in this way. And they don't only have to be accelerated, but they have also to be bent, because it is a round circle that they have there. So how can you bend particles? This can be done also by electric fields, but you have to put another angle. You have to put the field 90 degrees towards the path of flight. That's this second example. So we have an electron in a perpendicular electric field. I draw the parallel plate capacitor. It will look something like that. So this is my positive plate and my negative plate. And for easiness, I just assume that I have the electric field in between these two plates, and that outside I don't have any field, so I neglect these fringe fields. The electron will start here on the left and move to the right, but it's not along this line. The electron is moving along this line if I have no charges on the plates, but these plates will cause a force acting on the electron. So I draw this electron that I have here with an initial velocity v0 to the right. So it will follow this track until it reaches this point, and at this point a force acts on it. The force will be in this direction, and as long as the electron is inside this area, the force will be equal and always pointed upward. So we have a constant force, and therefore the path will be bent and the electron will make some turn, and after this turn it will continue its path on this dotted straight line. So it will be a parabola inside here, and if we look at the final situation, we still have horizontal our V0. There was no force to the right, therefore no acceleration or deceleration to the right, and therefore no change in velocity. However, there will be a velocity pointing upward. Let's call that V perpendicular. So I draw this perpendicular sign. And these two velocities together will amount to the final velocity, which is pointing to this direction. Let's write this down. Inside the parallel plate capacitor, a force F applies in y direction and causes an acceleration in y direction. So mathematically spoken, the force in y direction or in perpendicular direction is given as the charge, which here is the charge of the electron, times the electric field. If we have F, we also can use Newton's law. So therefore, this is equal to the mass of the electron times the acceleration, which will be perpendicular. And therefore, we can now resolve for the acceleration that will occur. It will be the charge of the electron times the electric field divided by the mass of the electron. The velocity perpendicular is then this acceleration times the time of flight. The time of flight, however, can be easily found since it is nothing but the distance over the velocity. And for the distance, we can simply take the length of this parallel plate capacitor from here to here. Why this? Well, the initial speed v0 will be kept during this flight, therefore this deflection adds a velocity in the upward direction, but if we only look to the straight direction, the velocity will be equal, and therefore the time of flight for this path will be exactly the same as the time of flight for the path where I turn off the electric field. You will get this as an exercise.